So we calculated, right? So now what we have done so far. Now we have calculated the potential energy of, firstly we calculated the electric potential and potential difference of different distributions, right? And then what we did, then we calculated the potential energy of different distributions. So we calculated the potential energy, right? Potential energy of different distributions. So first we calculated of two charge, right? So we had two charges, Q1, Q2, and then the separation was R. So we calculated the potential energy to be Q1, Q2 by R, right? And then we have multiple charges. So for the multiple charges, what was the potential energy? This was KQ1, Q2 by R12 plus KQ1, Q3 by R13 plus KQ2, Q3 by R23 plus so on. So these kind of combination. And we wrote this like half and K summation of I equal to 1 to N and the summation of j equal to 1 to n, I not equal to j, and then this was qi, qj, and rij. So this was the potential energy, right? And we calculated for the square, for the triangles, and for the different kinds. And then we calculated the potential energy in the presence of electric field. So we calculated the potential energy to be Q into V for a single charge. So there was a charge. So this was some electric field and some charge was it. So this has some potential at this point. Then the potential energy was this, right? And the fourth one, who has just
Sir,
joined.
sorry, sir, I joined late. Can you show the previous topic? I'll take a screenshot of it.
Yeah, so we didn't go ahead. I am just repeating what we did in the right. So what we have done so far, we were calculating the potential energy of different distributions, right, Pia? So this is what I was just talking about. So and
Okay, sir.
yeah, then we calculated the potential energy, right, of two charges. So of two charges in electric field, right? So this was what? This was K Q1 V1 plus Q2 V2 and then Q1 Q2 by R. So this we calculated. We had two charges in the electric field. This was Q1 and this was Q2 and separation of between them was R. So this we did. And then we calculated the potential energy of dipole, right? So we calculated the potential energy of dipole as minus P dot, right? And work done was what? So this was simply minus of PE cos theta, right? And work done was minus of P and E. This was cos theta 2 minus cos theta. So this was the work done for the case of dipole, right, guys? Okay, and now the next topic is what? So next topic is self interacting energy. What is this self-interacting energy? Right. So we understood that whenever we have, right, whenever we had 4-point charges, whenever we had 4-point charges, so there was some work done. There was some work done to bring those charges at these corners, right? So the work done to make the system, right? So this was we call the potential energy. This was potential energy. So what is the self-interacting energy, right? So it is the potential energy of the continuous distribution. Like sphere, right? Cylinder and these ones. So the EGC. So what do I mean by potential energy of these continuous distributions? So let's say you have a sphere, right? So case first is
Sir, it is continuous or continuous?
it is continuous, right?
Means,
Con-
sir?
continuous, right? Continuous, or we can say homogeneous distributions. So these kind of distribution. Okay. So case one is hollow sphere, hollow non-conducting sphere, or we have a hollow conducting sphere, or what do we have? We have a solid conducting sphere, right? So or right. These are the three kinds of sphere we have. So what is the peculiar thing about these spheres? What is the special thing about these spheres? Yes,
They all have self-interacting energy.
they have what? They have,
Self-interacting energy. It makes continuous distribution.
yeah, they are continuous distribution. Hollow sphere is a concept continuous distribution, right? On the surface, it is a continuous distribution. But what other? So I have written, right? This solid sphere is different. Distribution wise, solid sphere is different. And property wise, this non-conducting and conducting is different. But I have written these three spheres in the same on the same footing, right? So why I have written these sphere on the same footing? What is so special about these spheres? Why I have put them in the same footing, right? So can you guys tell me? We have already done this question in the when we were doing the potential. So I talked about this, right? So when we were doing the potential, then I talked about this. So can you guys tell me? Yes, remember. You guys remember or forgotten? Okay, so we have, right, we have this hollow non-conducting sphere. So all the charges reside on the surface of the sphere. Okay. For the case of solid conducting sphere as well. So if we have a solid conducting sphere, so all the charges for this case also reside on the surface of the sphere. There is no charge inside the sphere, right? No charge. So in here we have no charge, right? Inside we have no charge. For the case of hollow conducting sphere, we have inside this sphere we don't have any charge. So these are the same property of these three spheres. Understood? The charges remain on the surface. Clear?
Yes.
Yes, sir.
So charges remain on the surface. Okay. So now all the charges are here, right? So there would be some work done to bring all these charges on the surface of the sphere, right? So there would be some work done to make this system, and that is called the self-interacting energy. Understood? So work done to bring those charges on the surface, of work done to make this system, right? Work done to make this system. This is what we call the self-interacting. Is this clear, guys?
Yes.
Okay, so the proof is not important. We only need to remember that this is q square by 8 pi epsilon naught, and whatever is the radius. So this is the self-interacting energy of the hollow or conducting or non-conducting or solid conducting sphere. So please note down this part. Please note down this part. And whenever you guys have noted it down, now please step. Noted, guys. Noted. Yes, Aisha, noted. Fia, what about you?
Yes.
Yes, Fia, noted.
Yes, sir. Noted.
Okay, now the second case is that the second case is solid non-conducting sphere. Okay, so what is the self-interacting energy of solid non-conducting sphere? So we have a sphere, right? For the non-conducting case, the charges also reside. So we have this sphere, right? This is solid, meaning that it is filled, right? So we have this solid sphere, and uh, and the charges reside inside. Okay, and at the surfaces. Okay, so for this case, self-interacting energy, this is U equals to what? This is 3Q square by 20 pi epsilon naught. So this is for the case of the solid non-conducting sphere. Is this clear?
Yes.
The derivation is not needed.
There is no what?
Derivation.
There is no what? Yes, Pia, what did you say?
The derivation not needed.
Did we not prove this?
This is asking about derivation.
Oh, can you guys tell me what in the chat box? You guys are not audible here. So, what did you say? This is not in about derivations. Okay, okay, yeah, derivation is not important, right? Yes, yes, derivation is not. That's why I'm just skipping the derivation, right? Because we have to only they will only ask about the in the exam they will only ask about the self-interacting energy. They will not ask about the derivations. So that is why
Okay, sir.
that is why I'm skipping the derivations. Okay, so on the basis of this, we have one question. So you guys please note down this part and then we'll do one question. Noted everybody.
Yes, sir.
Okay, so we have this question, right? That we have two spheres. So one is this, right? And it has a radius. So it has a radius r. And we have another sphere. And this is minus. So this is q. This is minus q, right? So this is a conducting sphere, right? And this is non-conducting sphere. And this has also the radius r. And the distance between these 2 points, this is, let's say, 2r. Okay. So then we'll have to calculate what is the potential energy of this system. Okay. So is the question clear to you guys?
Will you explain again?
Yeah, so we have these two spheres. We have these two spheres, right? And these are kept at a separation of 2r. So the question is that what would be the potential energy? So what is the potential energy?
Sir, 3q square by 2 pi. We can apply that formula, right, sir?
Yeah, so okay, so you are partially correct. So for this one,
We need to add that 2 times, sir.
yeah, so we have okay, so let me ask this question, right? So we want to calculate the potential energy of this system, okay? But we have two kinds of sphere, right? So for this sphere, there would be some self-interaction, self-interacting energy. For this sphere, there would be some self-interacting energy. So they are interacting with themselves. They are interacting with themselves, but they are also interacting with each other. So we'll have three energies. Is this clear? Is this clear?
Yes, sir.
So two
Sir,
energies.
can you repeat how 3 energy?
Yeah. So one is that this one has some self-interacting energy, right? This one has some self-interacting energy. But these are two charges. So this is plus Q, this is minus Q. This is plus Q and this is minus Q. And they are separated by some distance. So they will also have the interaction energy, right?
Yes. Okay.
So that is why we have three energy. One, so we have two self-interacting, and this one interacting, right? So let us find out that what are the self-interacting ones. So for this case, this is a hollow one, right? So for the hollow one, what is the self-interacting energy? That is Q square by 8 pi epsilon naught R. Correct, guys?
Yes.
And we have this one. So again, Q square, 3Q square as Fia was saying, and 20 pi epsilon naught R. Understood? Here. And now we have this interacting energy. So that would be how much? That would be K and Q and minus Q by separation is what? 2R. Clear?
Sir, for first one, we did the positive self-interacting energy.
Yeah.
For second one, negative. And then for both, we did the general formula.
Yeah. So they are interacting with each other, right? For the first
Yes,
case,
sir.
they are interacting themselves. In this case also they are self-interacting, but they are also interacting with each other. But this minus sign, so we have minus Q and minus Q, right? So that will make it positive, so we'll get a positive 3Q square, right? So that is why we are getting positive. Understood? Clear?
Yes, sir.
Okay, so now let us solve this further, right? So this would be how much? So this is Q square by 8 pi epsilon naught R. This is 3Q square by 20 pi epsilon naught R. And this is 1 by 4 pi epsilon naught. This is minus here, right? And then 2R. And then we have what? Q square. So we have q square by 8 pi epsilon naught r, and then 3q square by 20 pi epsilon naught r, and minus of q square by 8 pi epsilon naught r. So this one cancels and we have 3q square by 20 pi epsilon naught. So this is the potential energy. Is this clear, guys?
Yes,
Clear?
sir.
Okay, please note it down. Whenever you guys want me to scroll down the screen, guys, should I scroll down the screen, guys?
Yes, sir.
Whenever you guys have noted it down, please tell.
Yes, sir.
Done. What about you, Fia? Noted.
Yes.
Okay, so now let us start the new topic, which is capacitance and capacitor. Okay, capacitor. So as you guys have already learned that what is a capacitance, right? Okay, so capacitance is what? It is the charge holding capacity, right? Okay. And then you have already learned about the what is the SI unit, what is the unit, or what is this vector quantity, whatever kind of quantity, right? So you have already talked about, you have already learned about in the CBSE courses, right? So now let us talk about the capacitor. What is a capacitor? Okay, but before that, let me talk about. So we have capacitance, right? So when we plot the charge, right, versus the voltage, so it comes proportional to the voltage, right? So when we remove this proportionality, so then we get C, right? So then we get this proportionality constant is called the capacitor, right? So C is what? Q by, and it is independent of the increase in the charges or increase in the voltage. So if I draw the plots, so if I draw the plots, so in this way, charge is increasing and the capacitance would be what? So this would be parallel line. And let's say if we have the voltage which is increasing, so again the capacitance would be parallel line. So what does this parallel line signifies? What does this parallel line signifies, guys? Yes,
Sir, it is static.
it is static, or you can say that it is constant,
Hmm, constant, sir.
right? So it is constant. Okay, so that is why this is a constant. That is why this is capacitance is a constant quantity. Okay, now we have right. So what is the capacitance? Capacitance of a spherical, right, distribution, or what do you say? Capacitance of a sphere, right? So this is a hollow sphere, right? So let's say that you have this sphere, right? So on the surface, what is the voltage? So this has radius r. So what is the potential of this sphere? Yes, hollow sphere. We have so capacitance of a hollow sphere, right? Right. So what is the potential of this hollow sphere? We have done so many questions on the hollow sphere. Potential, we calculated potential for different distributions, right? Yes, guys.
Yes,
Yes, sir.
sir. We calculated with the non-conducting and conducting.
Yeah, so this is a hollow sphere. So for the hollow case, conducting
We
and
have to minus both of those.
no. So for the case of non-conducting and conducting, the answer is C, KQ by R, right on the surface. This is the potential, right?
Yes, sir.
Okay, so then what is the capacitance? So capacitance is Q by V. So this is Q by K, Q by R, right? So this Q cancel and this is R goes in the, and this is K. So K is what? 1 by 4 pi epsilon naught. So we will get 4 pi epsilon naught R. So this is the capacitance of a hollow sphere, right? So This you
Yes.
have already learned in your CBSE classes. I am just revising whatever you guys have done. Right? So please note down this part. Right. So when you repeat all these things, then you will remember for a longer time. Right? Please note it down, and whenever you guys need me to scroll down, then please tell. Yes, should I scroll down the screen, guys?
Yes, sir.
Yes, sir.
Okay, so yeah, so you guys can calculate the capacitance of the earth, right? So take it as your home exercise, right? So calculate the capacitance of earth, and you guys already know that what is the radius of the earth? This is the radius of the earth, right? So you have this
Yes,
one,
sir.
then you can calculate the capacitance of earth. So you guys calculate and check what you get, right? So you can see there how much charge can our earth can hold, right? So that will tell you that how much charge can our earth hold. So yeah, you find that out and see how much charge can our earth can. Okay. Okay. So noted up to this point, guys.
Yes, sir.
Okay. So now we have capacitor. So this is what? This is an energy storing device. Energy storage device, right? And for our purpose, we will have how many kinds of capacitor? So we will have parallel plate capacitor. Then we learned about the spherical capacitor, spherical capacitor, and then we have the cylindrical capacitor. Okay. So in CBSE course, you guys didn't do these ones, but we'll do this in here. So let us first talk about the parallel plate capacitor, right? So for the parallel plate capacitor, we can uh, draw it like this, right? So we have these two parallel plates, okay, and we can join it to positive and the negative terminals of the battery. So this will give it positive charge and this will give it negative charge, right? Or what we can do is that we have a positive charge, right? And then the other one, we just earth it. So this is earth. So whenever earthing is provided, so this will create a negative charge, right? So this is Q
Sir, can you write in between
in between what?
or
Or,
or?
or. Okay. Yeah, and this is Q minus, right? So these are the two examples of parallel plate capacitor, right? So the parallel plate capacitor has one has positive charge and the other one has negative charge, right? So then it will have some capacitance. So let us try to calculate what is the capacitance of this parallel plate capacitor. Okay, so we already know that to calculate the capacitance, right? So to calculate the capacitance, what do we need? What do we need? Yes, we need charge divided by potential, right, guys? Is this clear?
Yes.
Yes. So we need to calculate charge. We already know charge is Q, and we have to calculate the potential between these plates. So we'll have to find out what is the potential. Okay, but what do we need know about? So we already know about the relation between the electric field and potential, right? So what is the relation? E is minus delta V by delta, right? So if we take positive, so E is, let's say the
Sir,
potential,
this one we can write it as dV by dr also.
yeah, so we can write this as minus dV by dr. Yes. But for the 2 points, we are calculating between two large points. For the infinitesimal, for the small change, we write a dV, but we are calculating the potential at these 2 points. So we will write it as delta V by delta. Okay. So yeah, this one is also correct, but this is infinitesimal change, right? Okay. So yeah, and the potential difference between these two plates is V, and the distance between these two plates is T, right? So this would be V by T. So V is what? E into T. Is this clear, guys? Is this clear?
So,
Now,
Yes, sir.
what we have to calculate? We know that the potential is electric field, whatever the electric field in here, and into distance. So we have to calculate the electric field in this region inside the two plates. Correct? Is this correct? So we have to calculate the electric field inside the plates. So
Yes, sir.
can you guys tell me what is the electric field inside the plate? What do you know about the single plate? So if you have the single plate, what is the electric field of this plate? Sheet, infinite sheet. So what is the electric field? Yes. Already forgotten, guys. This you have done in your CBSE class, right?
Yes, sir.
Okay, so let me just electric field is the first chapter, right? So to calculate the electric field, we already know that the infinite sheet or the sheet has, so in this way it is sigma by 2 epsilon naught, and in this direction it is sigma by 2 epsilon naught, right? So it has this kind of electric field. Am I correct? Yes, guys,
Yes,
correct.
sir.
Now negative one has what is the direction of the negative ones?
It will be opposite of this, sir. Minus
Opposite.
sigma.
Yeah. So magnitude would be same, but direction would be different, right? So this has outgoing.
Sir, there will be negative sign.
Yeah, there the negative sign will represent the direction, opposite direction, right? But magnitude would be simply same, right?
Yes, sir.
So this would be sigma by 2 epsilon naught. What in this direction? Okay, clear?
Yes, sir.
So now we have to calculate the electric field between these two plates. Okay, so to calculate the electric field between these two plates, let us write. So we have two plates, right? Or let me write it like. So we have this plate, this has positive, right? And this one is negative. So for this one, the electric field is what? Electric field is incoming. So we have this electric field and this electric field and this electric field. Correct? Is this correct? Understood, guys? For this plate, all the electric field will be incoming. Right? Understood? Yes, guys. Why you guys are silent? Is it clear? If it is not, then I will repeat it again.
Sir, can you repeat it again?
Okay. So again, let us go back to what we were studying. Right. So okay. So we already know that for the negative one, right? For the negative one, the electric field is incoming. Is this clear?
Yes, sir.
And this
And
is,
for positive part, it is outgoing.
yeah, and we have this positive part, positive part. Okay. So we have this region also. So this is inside, this is outside, this is outside. So in this region, due to this one, this will be again incoming. Is this clear now? Clear. I am writing about this one. We have three regions. Okay, so this is the parallel plate. This is the parallel plate. This is inside. This is outside, and this is outside. So how many regions do we have? This is one. This is second. This is third. So this is one inside. This is second. This is third. So in all these regions, for this one, the electric field would be incoming. Clear? So due to this one, this would be incoming, incoming, and in here incoming.
Yes,
Clear?
sir.
And for
Yes,
this
sir.
one, for this positive one, so in here this would be outgoing, right? In here this would
Yes,
be
sir.
outgoing,
Yes, sir.
and in here this would be outgoing. Understood? Clear?
Yeah.
Okay. So you guys can see that this part is cancelling, right? This is cancelling, this is cancelling. So in this part, this is adding. And how much is that? So we have sigma by 2 epsilon naught plus we have sigma by 2 epsilon. So how much is that? So electric field inside the region is sigma by epsilon. Is this clear? Clear? Yes, guys. Is this clear?
Yes, sir.
Okay. So
Yes, sir.
now we have voltage, right? And this is E into D. So voltage is E into T. So E is sigma by epsilon naught into T. And this is our potential. Okay. And what is this sigma? This is surface charge density, right? So sigma is Q by A. So let us plug that value. So potential is how much? That is Q by A epsilon naught and T. So this is the potential, guys. Clear? Clear?
Yes.
So now let us calculate the capacitance. Capacitance would be how much? This is Q by V. So Q is Q and V is how much? Q into D divided by E epsilon. Q cancel, this goes over here. So capacitance of a parallel plate capacitor is how much? Oh, so who wrote? Yeah, who is writing? Yes. So yes, guys. Did you understand this part? Okay, please note it down. So then we'll do this part you have already done in your CBSE course. I'm just repeating that. Right. So please note it down. And if you have any doubts, so you can also ask. And whenever you guys want me to scroll down the screen, guys, tell
Done.
done. This part also.
No.
Then, Via, what about you? Noted. Okay, then we have what we do is that. So what we do is that we put.
Sir, can you scroll little bit up?
Okay, so where? Yes, here is this okay?
Yes, sir, done.
Okay, so now we have what? What do we have? We have the capacitance of parallel plate capacitor when dielectric is placed between it. Right. So we have two parallel plate capacitor, right? And in between these two, we have a dielectric, right? With dielectric constant. So this is fully filled, right? There is no gap between these plates, right? So it is fully filled with this dielectric, and it has dielectric constant K. Okay. Then what is the capacitance? So yeah, so you guys have already learned about that whenever, so in the Coulomb's law, right? In the Coulomb's law, remember, take the analogy from the Coulomb's law. Whenever we had two charges, right? Then Coulombic force was what? This was simply K Q1 Q2 by R square, right? So this was Coulomb force. What is that? One moment, guys. Okay, so okay, so this is the Coulombic force, right? And this was equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. This was the Coulombic force when there were no dielectric. This was not placed in the medium. But when we placed these two charges in the medium, then what was the Coulombic force? Do you guys remember? So if we had Q1, Q2, and the separation between them was R, right? And this was placed in some dielectric medium. So can you guys, do you guys remember what was the F of medium? So this was F of air. What was F of medium? Yes. Do you guys remember or not? This is the first thing we learned in the first chapter. So this permittivity of free space, it is changed to what? Permittivity of the medium. This is E. And Q1, Q2 by R. So this is force of the medium, right? Do you guys remember now?
Yes.
And this is equal to what? This is equal to 1 by 4 pi epsilon naught and K, where this K is your dielectric constant. Right, so this K was your dielectric constant. Similarly, taking the analogy from here, so when we have this right, so when we had air between these plates, when we had air between these two plates, then the capacitance was A epsilon naught by T. So now if we have put the medium in that, so what would be the capacitance, guys? You guys can directly tell me the answer. So what would be the capacitance? Yes. So this epsilon naught will be replaced with epsilon, right? So then this is A E epsilon naught K by T. This is the capacitance of parallel plate capacitor when the dielectric constant is placed between it. Right? Clear, guys?
Yes, sir.
Okay, quickly note it down. So why are you guys not replying? I'm just repeating what you have done in your CPSC class. Right?
Yes, sir.
Okay, quickly note it down, and then we'll do one more type of parallel plate capacitor. Noted, guys. Noted.
Yes.
Okay, so now let us do one thing that what happens when we so the dielectric is or the capacitor is
Sir, for the dielectric one.
yeah the dielectric one, yes.
Yeah, yeah, fine, sir. Yes, sir, done.
Okay,
Yes, sir, done.
yeah, the capacitor is partially filled with the dielectric. And what do I mean by that? So in here, you saw that there was no any gap, right? But now what will happen is that the plates, right? So this is the plate, and it is partially filled. So we'll have this capacitor, which is with this thickness.
So, sir, will take half of that 1 by 4 pi epsilon naught k q and q2 by r square half will take.
No, 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 no. So we cannot do like that. So I will tell you that how we will calculate, right? Because in the case of Coulombic force, there were no partially filled or half filled, right?
Yes,
Okay.
sir.
But in this case, we can have this partially filled plate, right? So in that case, let's say that the thickness of these two plate is, let's say T, right? So this is the thickness. So we have two plates, right? We have right. So we have two plates. Okay. So we have two plates. Okay, and in between two plates, some mobile. Okay. So how will I? So this is right. So this is some thickness of yeah, dielectric is placed. So it has some thickness. This is the thickness, right? right? So this is, in that case, what would be the capacitance? So let us try to calculate the capacitance. Total distance is how much?
Sir, it will be D minus T.
So total distance is d, right?
Yes, sir.
So the non-dielectric one. So non-dielectric one is how much? D minus T, as you were saying. So air is D minus T. Clear?
Yes, sir.
Okay. So what do we know? We have to calculate the capacitance. And we know that capacitance is simply Q by V. So we have to calculate what? We have to calculate the potential between these two plates. Right? Clear?
Yes, sir. Yes, sir.
So this would be how much? Potential would be, this would be E, right? E of air,
Sir, we can take A epsilon naught D, right?
but A epsilon naught D is the case for when we have air only. So when we have
Okay,
air
sir.
only, right? Then it
Yes,
is.
sir.
But now
Okay,
this
sir.
is, yeah, this is partially filled with this dielectric, right?
Okay, sir.
Okay, so then because the potential would be different. Potential would be different because of this dielectric. So we have this dielectric of this thickness. This is the thickness, right? So the potential due to dielectric plus potential due to air. Clear? Is this clear?
Yes, sir.
And we know that
Sir,
potential,
it won't be V dielectric minus V air.
we are adding. So potential is, we don't have any negative charges, right? So these are all positive. So this would be
Sir, but
adding.
we need the potential only for the dielectric part, right, sir?
No, no, no.
Or all total?
We want to calculate the potential between these two plates, right?
Okay, sir. Okay,
So
sir.
it will
Yes, sir.
have this potential plus this air potential. Understood? Okay. So
Yes, sir.
for the case of potential, we know that this is simply E into D, right? E into whatever is the distance. Let me say as X or R. Okay. So for the case of dielectric one, this is E dielectric, right? And what is the distance? For the dielectric one, what is the distance?
It is T, sir.
D, right? So this is T. And for the case of air, so this is E air. And then what is the distance of air?
T minus T.
D minus T. So this is D minus T, right? Okay. And we know that what is the electric field of dielectric one? What is the electric field? So electric field, we know that this is sigma by epsilon naught. But if we have dielectric, so this will change to what? This is air. So for the dielectric one, what would be the electric field? This would be sigma by epsilon. Understood?
It is sigma by 2 epsilon naught or only sigma by epsilon naught, sir?
Because we have two plates, so in between there would be combination of these two. So inside it is sigma by epsilon naught, right?
Yes, sir.
So this would not be to, this would be only epsilon naught, right? Because we are calculating the electric field inside these two plates.
Yes, sir.
Understood?
Understood. That is permittivity of air. This is of medium.
Yeah.
Dielectric.
Yes. Okay, so this is sigma by epsilon T and this is sigma by epsilon and d minus. Okay, this is what? This is sigma by epsilon naught k and t plus sigma by epsilon naught d minus t. So we can take what is the common in here? What is the common? So sigma by
Sir,
epsilon.
sigma by epsilon naught is common, sir.
Yeah, so this is
So
common.
t plus d minus t.
This one. So we can write it. Okay, so this is we can write it in the conventional manner. So this is d minus t plus t by t. Okay, so this is what the potential. So now we have calculated the potential. So we can calculate the capacitance. This is what Q by, so Q and sigma by epsilon naught and d minus t plus t by k. And this sigma is what? This is Q by A. So Q by, and this epsilon node goes into S. This is, and this sigma is Q by A and t minus t plus t by k. So this gets cancelled and this goes over here. So this is A E epsilon naught by t minus t plus t by k. So this is the capacitance of a partially filled parallel plate capacitor. Is this clear? Is this clear?
Yes, sir, this is clear.
So this is partial one, and air one was what? Air one was A E epsilon naught by D, and medium was, or the dielectric one was what? This was A epsilon naught A by D. So these
D.
are the three cases. Please note it down. And if you have any doubts, so please ask. And whenever you guys want me to scroll down the screen, guys,
Yes, sir. Can you scroll down, sir?
done. Okay, so
Yes, sir. Can you scroll down, sir? Sir, can you show a little bit more up?
yeah, this one.
Yes, sir. Yes, sir. Yeah, yeah.
Whenever you guys have finished noting, please tell.
Yes, sir, done.
Number
Okay, so now let us talk about the next case when we have right. So when we have capacitor, right? Parallel plate capacitor, and when conductor is partially filled, right? So in the case of in the previous case we had dielectric, but now we have a conductor, right? So we have a conductor. So this is a conductor, right? So now we have to calculate the potential. Okay. So the potential would be V conductor plus V air, right? And what is the potential due to this conducting conductor? Inside E is what? E into T. What is this thickness? Right. So this is E conductor into T thickness. And what is the electric field inside? For the case of conductor, what is the electric field inside?
Sir, it's 0.
Zero. So V would be what? V would be zero. Understood?
Yes, sir.
So V is zero. Now we have only this. So this is zero, and we have only V air. So this would be how much? V air would be E into distance is how much? D minus. So this would be simply E D minus. This is the potential that we have. So then what do we have? The capacitance is Q by V. So this Q and V is E and D minus. So then E is how much? E is sigma or by epsilon naught.
Epsilon naught.
And again, sigma is what?
Q epsilon naught divided by sigma T minus T.
So this is D minus. Q cancels, so capacitance is how much? A epsilon naught by T minus. So this is the what? Capacitance of a conducting plate partially filled.
Sir, how A came?
So this is sigma. We have this sigma, right? So
Yes,
sigma
sir.
is Q by A.
Okay, sir.
So this is Q by A. So A goes in here. So this is what we have. So quickly, please
Okay,
note
sir.
it down. And in the next class, we'll do so many questions based on this. Okay. So yeah, please note it down. Please note it down, and then we'll do some questions. In the next class, we'll do questions.
Done, sir.
Done. Okay. This one?